So the experiment we are going to see today is again DC servo motor, study of DC servo motor, but we are going to plot the characteristics of speed torque characteristics and the back EMF speed torque characteristics. So this is the setup. In this particular setup, what you have is you have a DC servo motor and its own characteristics are given. When I say characteristics, it includes what are their rated voltage, rated current, what is their moment of inertia, and then it includes their armature resistance, armature inductance, back EMF constant, motor torque constant. All these are in the manual, right? These are fixed for the motor that we are having here. What is the setup here is the shaft of this DC motor is connected to this particular shaft. We are going to induce a artificial torque to it. So before that, there are two spring attachments that are here. One is pivoted and the other is connected to an adjustable knob. In addition to that, to this particular shaft, there is a disc, right? So some disc, something like this, where you have 12 holes inside this. Right? So 360 degrees, you divide it into 12 holes, right? So approximately 20-degree difference, you make a hole here. On this particular disc, on either side, on this side also and on this side also, you have different holes, and there is a laser light arrangement behind this. What is the need of a laser light arrangement is, as for one revolution, what happens is you will get 12 different pulses. These 12 different pulses corresponds to the frequency of rotation. So that we call it as a frequency to voltage converter, right? So there is a setup which is called as a frequency to voltage converter. So the voltage that is getting converted corresponds to what is your armature voltage. Okay, so that is one way of armature voltage that will be displayed over here. Either you can look at the voltage that is here, or you can use a multimeter to find the armature voltage. Okay, now what is the need for this FVC, that is a frequency to voltage converter that we had, was it will help us to calibrate also. What do you mean by calibration is, say for example, when you are using vernier caliper or something, first you adjust the zero readings, right? When you are looking at some convex mirrors, you try to avoid this parallax error by first initially adjusting it. Likewise, this system also requires some kind of an adjustment. What is this adjustment is, there is a knob that you can see here, which is called as a read knob, and read position and a cal position. Read position corresponds to reading, cal position corresponds to calculating or calibrating. Okay, now first let us do the calibration part. So when I switch on, what happens is, you can see here that it is in the calibrated mode. First thing that we must see here is the speed control. Now it is a minimum position. Don't look at the white position here. Now it is in the minimum position. This is the maximum position. Okay, so now this is in the minimum position. When this is in the minimum position, what does this mean is, this is a direct DC speed control. It is a variable DC power supply. Variable DC power supply means this motor will rotate based on the voltage that I have applied, which means that this knob, it is like a small high resistor that is connected here, and now in this position the resistance is at a maximum position, so it is not allowing any current to flow into your DC motor, so motor is not rotating. As I slowly increase this, what happens? I am giving some amount of voltage into my DC motor, so a small amount of current is flowing, and correspondingly the speed also increases, right? So indirectly, what is the speed control technique? This is called as the direct resistance speed control technique for DC motors. So now your speed control is in the maximum position, and it is running at it is actually running at 1400 RPM, but this is not the correct value. Why this is not the correct value? Because we have not calibrated our settings. So in order to calibrate it, what you must do is move this position to calibrate, right? So this complete setup has been calibrated by the manufacturer to operate at 500 RPM. So this is just a 454 RPM. So first thing that you must do to get the correct answer is adjust this such that you get 500 RPM. Yeah, this is 499, 500 is so. Yeah, I think this is fine. 499, 500. So now we have calibrated, right? Once we calibrate, do not come back and use this particular knob. Once calibrated, it is done. Now move to the reading mode. Now this is the actual RPM of your machine. It is 1542 RPM. So now, okay, the machine is rotating. Now based on the disc that you are having and the frequency to voltage converter, you are having an armature voltage of 9.54 volts. So this is the armature voltage between this. Or if you don't believe this frequency to voltage converter, then what you can do is you can use a multimeter and check also. That is also fine. And this is your armature current. Armature current, where are we measuring? From this ammeter here. There is an ammeter symbol here. So it is directly connected, and we are having 0.14 ampere of armature current that is flowing inside this. This is a separately excited DC motor. You can see here that there is a constant voltage fed to the field winding, and it is separately excited DC motor. Now what is our objective? Our objective is to plot the speed torque characteristics, which means that speed is here. We are going to change this particular torque. Now what will happen? You must analyze what are the things that are going to happen. As I put this particular torque, what happens? There will be an increase in the load of your DC motor. When there is an increase in the load of the DC motor, it will draw more current. Am I right? So as we put a larger load here, as we increase the torque, this current is going to increase. At the same time, since we are loading the motor more, its speed will decrease. It is like a person is on a running track. You put one school bag on him, right? He will run slightly slower. You put two school bags on him, his speed will reduce. It is some similar logic, analogous logic. So these are the initial setup. What you must do is, what you must tabulate here is, you must tabulate. First, radius is already given from the manufacturer. First, set your armature voltage VA. Okay. Now armature voltage is what is this? 9.71 volts. So for a given 9.71 volts, you are going to do all the, what are the things that you are going to do is T1, T2, that is torque 1, torque 2 with this knob and this particular knob, and their difference T1 minus T2 multiplied by the radius, and then the speed you are going to measure, armature current you are going to measure. So you will tabulate it. As I increase the torque, right? See, as I increase the torque, you look at these two readings. This will increase and this will decrease. I am increasing, see, from 0.133, still I am not loaded actually. Now I am started loading. The string is getting stiff. So it is 0.139, 0.14, the speed is reduced, 1550. Your current is increased, it is decreased, still 0.145 ampere, 147 ampere, 1527, speed is decreased. Now as you keep on increasing, my simple question is, what will happen to the maximum torque that you give? It is like a donkey is carrying boxes. You keep on putting boxes and boxes and boxes over this donkey. After some time it will stop. Am I right? Same thing will happen here also. As we keep on loading, what happens is maximum current will start flowing through this. When maximum current starts flowing through this, this armature winding will be damaged, right? And obviously the speed will come back to 0. So always while loading this, you must make sure that this current does not go beyond the rated current of this DC servo motor. So what is the rated current of this DC servo motor? It will be given in the manual, or in otherwise the rated torque of this voltage is 11.85 kilogram centimeter, right? So it is already given. So you cannot go beyond 11.85 kilogram centimeter. How do you get 11.85 kilograms per centimeter, it is mentioned here that 1 kilogram multiplies 5 grams. So on one side you have these 1 kilograms and you cannot go beyond 11 kilograms. You cannot. So now we are at 750 grams. If you focus here, you can see now we are at 125 grams. Right? We cannot go beyond 11.25, that is 1125, we cannot go. So you can see that your current is also increasing to a larger extent. So just to show you the maximum value, what I will do is I will switch off and then I will show you the maximum value. So I am switching off the motor, right, just to show you till what extent that you can go. See that this is for 1 kg and this is also for 1 kg. I have removed this. So alright. So by changing this particular tar, so you will tabulate this. So what we get is you will be plotting two characteristics from this. One is speed and the torque and the other is torque and your armature current. So the model graph that you will be having is this one. A speed torque, armature torque characteristics you will have, obviously they are all linear characteristics, so you will have a linear slope like this. And the speed torque characteristics, as you saw that as we increase the torque your speed actually reduced, right? So you will get such a kind of a characteristics. You can repeat the same thing. You can repeat the same thing for a different armature voltage also. And how do you change a different armature voltage? By changing the speed control knob. Say for example, by keeping the speed control knob, I did the complete experiment. Likewise, I can keep my speed control knob in the middle such that my armature voltage is only 6.8 volts, and then you can repeat the complete experiment. So likewise, you can have different characteristics for speed torque and this torque armature current characteristics. So this is the first part of the experiment. Second part of the experiment is you will plot the back EMF versus speed characteristics. In the back EMF versus speed characteristics, you bring back this to the null position. You bring back this to the null position. Now what you do is you adjust this particular, so very straightforward in the sense, keep this to say minimum voltage in the sense your armature voltage is 0 now. Now you increase this particular voltage. As you increase this voltage, note down your RPM here. So increase your speed control voltage to a maximum armature voltage here and then monitor your RPM. So it is a very simple back EMF characteristics, but you may ask me where is the back EMF, right? Back EMF you have to calculate from this particular formula. What is that? You will increase the speed control knob, right, so that the speed is increased. When the speed is increased, you will monitor the armature voltage and armature current also. Armature voltage is noted, armature current is noted. So these are the three things that you will monitor from the experimental setup. These two things you will calculate. Omega is your angular velocity, which is 2 pi n by 60. So n you take it from this column. And then you will calculate your back EMF, which is VA minus IA RA. VA is here, IA is here, RA is also given in the manual, so you can calculate your back EMF. So once you calculate your back EMF, so between back EMF and speed, you can plot the characteristics. So this is what is about the DC servo motor is, right?